The ICEVI, the Nippon Foundation Mathematics Package for Teachers video series, Abacus as a Mathematical Tool. Title of the video: Square root of an 8-digit number involving 5 zeros as the lower digits. Example: 12,100,000. The purpose of this problem is to give experience to the child on how to deal with larger digit numbers when we do the square root problem. As indicated in the earlier exercises, when we have higher digits, the entire calculation cannot be handled by a single abacus. Now the purpose of this calculation is to show that 12,100,000 is not a perfect square. When it has a remainder, it automatically indicates that one has to go for further calculations to get the decimal digits of the square root that can be done separately. Moreover, in the process of finding out the square root, there will be a number of calculations within calculations. So we will get the result in every stage, and for the details the child may have to do the calculation at every stage also. Therefore, the purpose here is to explain the procedures involved in finding out the square root of higher digit numbers, and the actual calculations can be done by using another abacus too simultaneously. For the purpose of calculation of the square root, let us group this number into 4. The first group is 12, second group is 10, and the third group is 0, 0, and the fourth group is 0, 0. Before we start, let us set the number in the abacus. As mentioned, we cannot go for the digital calculation using this abacus as we do not have sufficient columns. But we will prove that this is not a perfect square, and the further calculation leading into the decimal digits can be found out using another abacus. Now let us start setting 0 in the right extreme, then the second 0 to the left of it, third, fourth and fifth, and finally 1 after the 5 zeros in the sixth column from the right, 2 to the next of 1 and 1 to the next of 2. Take the first group 12 and consider the perfect squares there. 4 and 9 are the perfect squares in 12. Now 9 is the highest perfect square, and take square root of 9, which is 3. Set the square root 3 to the immediate left of 1 because 3 is larger than 1. Now multiply 3 with 3, which is 9. That should be subtracted from 12 and you get 3 as the remainder in the first set. Now you are left with 3,100,000. In the next stage, you have to take the remainder of the first group and the second group. In this case, it is 310. Before we go for the calculation, the square root 3 should be doubled and set the 6 in the extreme left of the abacus. Now consider 31 of the 310. Now ask how many 6's in 31. You get your answer as 5. It is safe to reduce 1 and consider 4 as the assumed quotient. Set the number 4 to the right of the first digit of the square root 3 and to the right of the number 6, which is set in the extreme left of the abacus. Now multiply 4 with the 64. That is 4 multiplied with 6, that is 24. That should be subtracted from 31 which gives the remaining number as 7. If we add the 0, the remaining number you get at this stage is 70. Now 4 multiplied by 4 is 16, which is reduced from 70, and then you get the remainder as 54. Now you are left with 54 in the second group. Now you have to add the third group, that will become 5400. Look at the square root now. It is 34. This should be doubled, and therefore clear the 64 and set 68 in the left extreme of the abacus. Now consider 68 and 5400. As the dividend has two zeros and the divisor closer to 70, you can always use a shortcut and ask how many 7s in 54. By saying 7, you can set the 7 to the right of the square root 34 and to the right of 68. In case the assumed quotient 7 is wrong, then the calculation itself will show. Now multiply 7 with 687. You can use another abacus too if you want to do a separate calculation for this. We are just explaining the procedure in this exercise, and therefore if the child needs to do the calculation, another abacus can be used. Now the multiplied value of 7 and 687 is 4809, and this can be subtracted from 5400, and the remainder you get is 591. Now take the last two zeros, which is belonging to the fourth group, and the remainder we get at this stage is 59,100. We have to double the square root 347 at this stage and set 694 in the left extreme of the abacus. As the first three digits of the dividend are closer to 600 and the first two digits of the divisor are closer to 70, we can consider these two numbers for just getting the assumed quotient. These types of shortcuts help when we are dealing with the higher digit numbers. As there are 8 sevens in 60, we can either take it as it is or reduce 1 and take the assumed quotient. Let us set 8 to the right of the square root 347 and making it as 3478. We have to set the 8 to the right of 694, and now you have to multiply the 8 with the 6948, which you can use a separate abacus for calculation. The value you get is 55,584. When you subtract it from 59,100, you get the remainder value as 3,516. The whole number of the square root that we have got so far is 3,478. You have a remainder which is 3,516. This indicates that the number 12,100,000 is not a perfect square. Now, in order to get the decimal part of the square root, you can start adding 0 to the remainder in every stage and use the divisor, which is double the value of the square root, and adapt normal division procedures. When you do this, you will get the decimal portions, and in this case you get the decimal portion subject to correction of 2 decimals is 0.05. Therefore, when you add this with the square root which you have already got, you get 3,478.05 as the square root of the number 12,100,000.